Hey there, welcome back to Intro to Cognitive Science. Today we're going to continue our journey through the early steps of cognitive science as a field and how we got away from the behaviorist approach and into a better look at, hey, what is the nature of the thing that's actually doing the information processing? So far, certain things can't really be explained in the behaviorist framework, right? Basic motor plans, the top to bottom, like I have to plan some execution pattern, but a lot of my muscles are going to have to talk to each other up and down along the way. There must be something happening there, some kind of feedback, some kind of hierarchical programming. And latent learning, so learning things in a non-goal directed way, just learning things because you pick them up from the environment, not because something happened to you or because something triggers a specific unconditioned response, right? Language is a particularly good example of something that has not been able to be well explained. The structures that we use to manipulate and understand language internally, there's some way that we're using all that information internally. We're doing something between the time that the words hit our ears and our response sentences come back out to make sense of the patterns. So it's not just a stimulus response chain. The Turing machine on another vector comes in and says, hey, here's a way we could think about looking at the structure of a processing system to move symbolic information around in a physical way. So we can bring all this stuff home together. The idea that we are trying to, the brain must be doing information processing in some of these cases, and put it together in the idea that there is a physical way we can do that. It's in our neural systems. But the question is, how do we build tasks, experiments, to understand these things? To start, let's get into a little bit of information theory, a bit, if you will pardon the pun. So the Turing machine brings up this concept of, we've put together an understanding of information processing as a whole system, right? But information is pretty broad. You might think of a library, all the text available, the internet, like your phone number, right? Like you have all these different ways of capturing information, but they're so broad, and so some of them are whole books and some of them are single words. What is information? What's the basic unit of information? And if we know what the basic units are, how do we manipulate and move those units around? And then how might any of that play out in the actual brain? So, what's information? The best definition I've encountered is any distinguishing signal that resolves uncertainty. The most basic unit being the bit. You've probably heard of these. Ones for yes, zeros for no. The bit. Everything in your computer or your phone or wherever you're looking at this video from is moving bits around to paint the screen, to display, to make the speaker vibrate, to give you the sound. All of that is ones and zeros moving around, resolving uncertainty, giving something to do that's not random noise. So we combine these to make more complex signals. So you can have 2 bits, has 4 possible states, 0, 0, 0, 1, 1, 0, and 1, 1. 8 bits has 256 possible states. Okay, cool. So let's kind of throw some of this at the wall. How much information do you need to communicate the result of a coin flip? Well, a coin flip, barring extremely rare circumstances, is going to be in one of 2 states, either heads or tails. You would need 1 bit of information to represent the number of possible outcomes. And so then if you said, tell me the result of the coin flip, all I would have to say to you is 0 or 1, assuming you knew which one meant which. We'd have to assign that ahead of time. But a coin flip contains 1 bit of information. How about a zip code? Well, Oswego zip code is 13126. If you know anything about zip codes, the idea is to break the number of human beings living in areas up into roughly equal sizes. In most places, I think overall that we use most of the zip codes, but there's still some space. But maximally, it's 5 digits, so that would be 100,000 zip codes in the United States. Okay, cool. That means... Oh, right, so 5 digits, 100,000 possible values. For me to get you to Oswego, we'd have to convert this to binary, right? We're trying to do this in terms of bits, the basic information, 1s and 0s. So, to do binary, to do 5 digits, to do 100,000 values in binary, comes out to this. That's the actual binary for 13126, 13,126. It's the same as digits. It's just instead of maxing out at 9, it maxes out at 1. Just your little common sense lecture of this for the day. So, 17 bits. We need 17 bits to transmit your zip code. Okay. So, I hope this is illustrating the idea that we can encapsulate information in these very basic units, single bits. We can do that with symbolic information, numerical information. We can also do it with non-numerical information. So, actual symbols. You know, I can encode words into bits. In fact, that's how these words are being displayed to you. The system I use to type them stores the bit string, and then when it comes time to draw the screen, it draws the text correctly, right? But this goes everywhere. It goes to images. Images are just loads of numerical values, which can be represented by bits, and the color pattern, right? It's all reds, greens, and blues, or I guess yellows, periwinkles, and chartreuses, or whatever there's a more modern take than just RGB. But the idea is that the amount of light on whatever system you're using right now, for each pixel, is just a numerical value. An image can be made up of numbers, which can be made up of bits. The same is true of audio pitch. Like I said, color, brightness, all of this can be bits. Computers do this all the time. As I said before, they're doing it right now. But the idea that this spreads out is that everything that we do experience is informational. So, cool, we can catch audio and vision and even internal symbols, but we can also catch, potentially, flavors, sensations, smells. There's work, not very popular lately, but there's work going on to try to get an artificial smell generator for various systems. It's a little bit wild, but the idea is like I could combine basic smell elements and try to create composite smell elements, just like I can combine bits of light into a image on the screen for you. So, this is the idea. A lot of what we experience is informational. A lot of what exists is informational. Anything that is not noise, just random patterns, is information. The things that you touch signals actually too. That's another element of this. The amount of pressure you feel on your hand if you poke it could be represented in a numerical way. So, information exists. I hope I've convinced you. And it has the most basic unit that we can use to capture information is a bit. There's more to it than that, but that's the basics. We also need a way to transmit information if we're going to move it around. So any medium that transmits from sender to receiver. Shannon's model has this. There's a source, that gives some information to the transmitter. The transmitter is attempting to send that signal along to the receiver, but there's also always some kind of noise. So if you think about this in terms of vision, think about looking out over the horizon on a clear day. There's a very low noise source, and you're getting all the light signals just right. But on a more hazy day, there's a lot of diffraction going on. You're losing some of the signal, but you still see it. You still can make sense of it. So there is still signal there, but it is diluted by the noise. So the idea that not only does information exist, but it must travel to us. It must infiltrate us somehow for us to be able to use it. That's key. So, how are humans do this? Cool. We can quantify information, and we have some idea of what the transmission process is like. What's this like in the brain? And we can conceive of, as I said before, all of the human senses could be thought of as information channels. Somehow, the signal from the world is getting into the brain to be used for something. And so one interesting way that we can apply a scientific method to this, that is common, is find the edges. If we want to better understand these human senses as human information processing channels, what are the limits of those processing channels? So, that's what we will do. Some experiments were run in the history here to examine the channel capacity of these human sentences. So, like, what's the bandwidth? How much information can you pipe through at a time before it starts to get a little bit too much for the stream, right? The bandwidth of the channel. And then what are the limits in terms of the amount they can carry in general? Maybe how much we can store in memory. And so we get into studies of absolute judgment and absolute memory. So what are those? What does that mean? These are our route to understanding the limits. Absolute judgments. So absolute judgments try to capture how much information can we transmit by making someone, a human, a person in one of these tasks, categorize colors or identify pitches of sounds. The idea being that you have to make a judgment. So you have to have some kind of storage that keeps track of some sets of values until we run out of the ability to do it. So what does that all mean? Well, first, I'm going to play a short video of the range of audio values that human beings are capable of hearing. Turn your volume down a little. We're going to go through this. It's quite interesting. So I'm going to mute myself, and we'll do. Ow. Sorry about that. But it's worth hearing. It's worth experiencing, because now you can see where you begin to hear sound and where you can no longer hear sound. Numerically, 20 to 20,000 hertz are the frequencies of sound that we are capable of hearing. I know that sucked. It hurt. But that's the range of your hearing. So these are the values you can keep track of. Now, the idea of the experiment is, if I present to you tones somewhere along this continuum of values, are you able to actually distinguish which one was which? Are you able to keep track of a number of tones? What's the maximum number of tones you can keep track of before you start to get confused? So That's the Pollock experiment. Select various values of tones in the range, and then you can imagine two tones would be fairly easy to distinguish, right? I can tell which one was the high one and which one was the low one. But if I give you 14 different tones to keep track of, that starts to get a little bit more tricky, right? So that's where Pollock went with this, and the idea of Pollock's work is to figure out where do we max out in terms of our ability to correctly identify pitches. And the idea here is, what we found is that we max out at around 7 different tones before it becomes kind of more or less chance at us being able to identify which tone was which. So 7 different values to 7 possible states. The thought was that around 2.5 bits of information is what we are capable of storing for this particular task in terms of keeping track of absolute pitches. 2.5 bits might not make sense because that's what's half of a bit, but the idea is just to bits are the density of the information at the most basic unit. It's a little more complex than that. So, you can represent more values than just 2.5 bits, but not much more. So, the idea of this study was, it seems that our audio channel informational capacity is 2.5 bits. Okay. Interesting first finding. This is giving us a numerical way to understand some of the information processing that happens at the front end of our experience of sound. What about our experience of memory? So less about categorizing and identifying possible differences of like sounds out in the world, but what about storing and retrieving information? This would similarly need to move information around across different channels in the brain. But the question is, how much information can we store in short-term memory at a time? So this is the list learning task. Sorry, I bumped the microphone. Memorize what I show you right now. What were they? In what order? XQT. I know I can't hear you, but I'm giving this the space it needs to breathe. So XQT, that was easy, right? You were able to keep track and store and hang on to those 3 little symbols pretty easily. Let's do it again. What were they now? Gets a little harder. AMVCYSRPBA. So this is about the range, about the best that folks can do before it just gets too hard and the letters start to slip out the back. And not just the back, actually there's a primacy and recency effect. You'll remember the start really easily, and you'll remember the end really easily, but the middle ones get a little foggy. So this is another example of an information channel capacity that actually is about 7. This gets us into an interesting little foible of a lot of psychology research that shows there is this interesting thing about the number 7. We seem to have a lot of capacities that are limited to about 7 items, give or take a couple. And the idea is that our information channels have these limited capacities. And maybe it's a common structure that we use throughout the brain. Maybe there is a common, band of neural fiber that happens to be able to carry about 7 distinct patterns. So our absolute judgments of colors and sizes as well as the sounds are about 7. Items in memory is about 7. This is fascinating. This is an interesting commonality of how information processing seems to be limited throughout the brain. It's not hard and fast. There are tons of examples of things that are not 7s. It's just an interesting collection of ideas. If you look up Miller's magical number 7. But there's something more to the picture here that undermines the idea that we have these very consistent limits. Hayes shows in a study shows that we still maintain 7 item capacities, channel capacities, whether we're asking people to memorize bits or whole numbers or letters or entire words. How? A bit is the most basic unit, and a word must be represented by tons of bits. We need lots of information in terms of the raw amount of information available to make sense of a word. So how the heck does the capacity remain around 7? These lines, as you can see, they all kind of overlap. Our use of words versus our use of bits and numbers, we have the same performance on these same kinds of memorization tasks. How could that be? Well, there's a concept in memory known as chunking, and this is big. I guess it's not just memory, but it's often human memory. Beyond the basic bit, we seem to actually store information in these ideas called chunks. They're more complex globs of information that hang together. They activate together. They go together. It's not just like distinct, separate ideas. They hang together. Here is an example of this process in action. Here's 10 numbers. If I asked you to memorize these, it would be a little bit of a slog. I just told you it's kind of at the limits of human channel capacities, right? A little bit beyond. 7, 4, 3, 9, 5, 4, 9, 5, 3, 2. But what if I presented them to you like this? Oh, shoot. That's a phone number. It's not my phone number, but it is someone's phone number. These are just random numbers. Don't call this. It's a phone number. And we know phone numbers are way easier. But why? What on earth allows us to store the same information, 10 digits, into a structure that is just easier to remember for whatever reason? That's the idea of chunking. So we have created over our lifetimes these memory structures of understanding, those are phone numbers. Those have the area code as one piece of it, which has its own distinct experience. We have I actually forget what the second chunk of numbers is, but the 3 and the 4 going together somehow makes it easier. It's easier to memorize a 3-digit and a 4-digit. So these are memory structures that we've built that bundle all the information up into. It's not smaller. All the information is still there. It's still retrievable when we think about the phone number, but it's not. It doesn't take as much of your channel capacity to pull it out. It's 3 bits or 3 values instead of 7, instead of 10. Chunking is an interesting phenomenon, and I think it illustrates that there's a difference between data stored and access signals, especially if we look at some exceptional memory. So Anders Ericsson, 1991, two participants learned this same kind of simple digit span task. The interesting thing about them was that they were both track runners, and they blew up the magic number 7 and the previous findings of small numbers, right, of small channel capacities on this, because they weren't using the channel anymore. They were building these deeper memory structures. In particular, they were using things like good run times that they'd had in track. They had an access to a lot of very familiar numbers that they were able to compile into their memorization tasks. So they could reach spans of memorizing 80 digits at a time. They could sit down, have 80 digits presented to them in the same rate, slow rate that I did to you, and they could memorize 80 of them correctly and spit them back out. They wouldn't keep them forever, but they were able to keep track of them because they were using this chunking concept. So, when it comes down to it, chunks seem to be a fairly basic unit of information, at least in the brain. I wouldn't say that it doesn't mean that we have infinite capacity just because chunking can chunk chunks and we can store information in chunks of chunks of chunks, but something about the way that our brain moves information around is able to move chunks or use chunks or access chunks using a single bit of information, even though the chunk itself contains much more than that. So the channel capacity might be limited for how we access chunks, but what do we actually do with the information when we access it? Here's another interesting foray, thinking in terms of filtering attention. So we're going to watch this video. Moment. Yeah, just watch.
This is an awareness test. How many passes does the team in white make?
Go!
The answer is 13. But did you see the moonwalking bear?
Go!
So that's a bear moonwalking public service announcement about cyclists from Britain. But this is actually a famous experiment. This is a little bit of a silly version of it, but the idea is you have a limited capacity to focus on information as it's coming in from the world. This is famously known as the gorilla experiment. In this case, it used a bear, but the original used a gorilla. So we are focusing. There's a lot of information moving around in the video, on the screen. So we end up with this task of focusing on, hey, where's the ball, and where are the white shirts, right? We're juggling some information there, trying to parse the scene out. So the costumed figure, especially because it's in a dark costume, it just falls by the wayside. Now, some of you might be patting yourselves on the back. I saw the bear, haha. But of course, that's possible. That's not impossible. But the idea is the odds are good that you missed it. And this is showing the idea of selective attention. And this is a key mechanism throughout the brain for how information processing can work. So given that there's so much information available in the world and internally in the brain, say in terms of our memory, landscapes of memory and all that kind of stuff, we have to be able to take our narrow channel capacities and point them in the right places. And that's selective attention. So, again, can be in the environment or it can be internally. Here is a model presented by Broadbent of how this might work. So sensory input comes in on the left here, and it goes into a very short-term memory store, something that will decay quickly and we're going to lose track of it. And then it goes through a selective attention filter, which goes to our limited capacity channel, right? Remember, we have limited capacities for vision, for sound, for memory, all this good stuff. And that then goes on to some other internal mental process that helps us make sense of the world. But it also helps us reset the attentional filter. So this is, you don't have to memorize this model. This is just to illustrate the idea that somewhere in the process of information flowing into our brains, there must be a step at which we make a judgment. Not we, some piece of our cognition makes a judgment about which parts of the world are salient right now, or which parts of the world are relevant to what we're doing. This is also illustrated in the cocktail party effect, if you've heard of this. So imagine you're sitting in a noisy crowd, and first of all, it's kind of remarkable that you can actually focus on the conversations that are happening in front of you, right? You are employing your selective attention to filter out all the junk sound that you're hearing in the room, other people's conversations that aren't relevant to you, so that you can focus on the one that you're having in front of you. This gets a little harder in online audio, as we've probably all noticed by now, but here's the thing. If someone 2 tables over says your name, you notice it. You can tell. Why? How? I thought we were discarding all that information. Where's the step where my brain gets to jump in and say, oh, wait, something important was in there. We got to go back. There's so much information in the room, and we were even filtering some of it out, but you're still getting it. You're just actively rejecting it. And part of you is capable of monitoring it for really important stuff. So, let's watch another video. This is interesting. There's a guy, he's a psychologist, I'm sure he's demonstrating this effect. You can guide your own attention in this way. So, first, focus on the guy on the right.
All right, so today I'm going to talk about 4 things. These are the 4 critical things to remember. How the first relates to how we make mystery. For me, it's kind of strange because the second thing is perception. The third thing is memory. The fourth thing is knowledge. That's going to change. I'll warn you. So what I did was I ate a lot of Czech cereal that way. I got a Czech cereal magic. What are the big? And that made it really great because that way I could eat perceptions, memory tricks, and then I'll do them for my friends. The big, you know what I mean? Okay.
Okay. He was talking about something about memory and some very academic-minded something else, right? I'm going to play the same exact information, the same video back to you, and ask you to focus on the left guy.
All right, so today I'm going to talk about 4 things. These are the 4 critical things to remember. The first relates to how we make mystery. For me, it's kind of strange because the second thing is perception. The third thing is memory. The fourth thing is knowledge. That's going to change. I'll warn you. So what I did was I ate a lot of Czech cereal that way. I got a Czech cereal magic. What are the big? And that made it really great because that way I could eat perceptions, memory tricks, and then I'll do them for my friends. The big, you know what I mean? Okay.
Okay, and that one was about like chunky clothes and Czech cereal and whatever. But you notice that you don't remember much of that, but potentially. I don't know your exact brain. Maybe you have an amazing mind that's capable of grabbing all the information at once. But you picked up things each of those times in a different way, even though the information available in the world was identical. You just did something different with it. So that's the cocktail party effect. And it's investigated empirically using these dichotic listening tasks. So similar to what we just showed. The idea is like, what the question being, what kinds of things trigger these differences? So the dichotic listening tasks were better at filtering out information from people who are speaking different languages, right? Well, actually, from gender, so more or more feminine voices, they're easier to separate out. And then semantics, like if someone's just babbling meaninglessly versus actually producing speech, that's another way that we're able to separate the information better. We're able to partition them out. Even though they're all overlapping chaotic masses of information in the same way, we just have a better tuned system for separating these things out. And these may differ by culture. Like, you know, a lot of these findings, you got to remember that there is a lot of work to be done to figure out how far spread they are. But these are just some interesting tokens of language. Even though it's all just noise, we're able to separate out, oh, this is a language I know, this is a language I don't know. Or even if I know both, right? Genders, you know, I'm sort of used to parsing masc and femme voices. Semantics, I'm used to actual words far better than just random gibberish. But you're able to focus and separate them better based on these features for some reason, for whatever reason. Most likely because of skill we've picked up. We've grown into environments where these things are useful differentiators. So the selective attention model is this idea that the information processing that we're capable of actually doing is broken into stages. So information comes in, sometimes we select specific pieces of it, and we can do that during multiple stages of processing. So it can be at the front end for what I'm literally moving my eyes toward. It can also be in the middle step of like, hey, what am I actually going to let into like my bigger processing abilities? And even sometimes fully internally with, hey, what am I actually going to think about? I've got a lot of thoughts bouncing around. Which one am I going to focus on, right? Focus. Anytime you focus, this is selective attention. But there's still a lot to figure out about the way all this works. And I'm not talking about in this course. I mean in life, in science. We are still figuring all these things out. There's lots of good research to be done. So that brings us to the end of our discussion of human information processing. Well, for this lecture. Of course, the rest of the course will have tons of that in it. But we have these pretty well-defined capabilities, right? When it comes to moving information around, we have these sort of limited channels through which we move that information, or at least activate or access that information. And we have limits. So to overcome those limits of how we move information around, we have the ability to selectively attend to things while we interact with the world. So, that's it for today. Final thought? What other kinds of attentional filtering do you employ day to day? All right, thanks. Take care.